Thank you. All right. So we'll have Awanish today talk about how to control the motors, especially the BLDC motors and the stepper motors. And we want to kind of see that in action by looking at how he does that using ROS codes and ROS commands. And we'll try to see whether how that can be seen in action. So it's a little bit of a presentation followed by a demonstration. I was really hoping that we could do the demonstration in a much better way by sharing the screen for the commands. But for today, we will go with trying to go ahead with capturing it on a mobile. All right. Okay. Off to you, Awanish.
Okay, thank you, sir. So, am I audible? Or
You can bring the laptop to this side, sit down here and view the presentation.
He's busy, should have already.
Okay, Rakesh. No problem. We'll have it later.
Shall I unmute here or the sound is here? Okay.
Is he audible from here?
Hello, everyone.
Yes, he is audible.
Okay, right. So, yes, today I'm going to talk about the onboard system.
Yes.
How it looks like of a ship model. And then I'll be just walk through that how we generally communicate between, the main processor and the controllers, and then we have stepper motors, BLDC motors, all that how we are going to communicate. That's I'm going to cover. So, this is how the basic architecture look like. Okay, we have main processor. We call it as a processor. It has it's a Raspberry Pi. Then we have a microcontroller which does the dedicated task. I will tell you why we are using this separately. Then we have onboard relay, which is like 8-channel relay. I'll be talking about what exactly it does. And then we have one stepper motor with the drive, and we have BLDC motor with the drive. So this all has to be controlled either manually or with a feedback. So we have a base station computer here. So on the right hand side, so there are two controls. One is through joystick, and another one is through the SSH. You do the SSH, get into the Pi board and execute your command. So, and the other one is the RF, which is like, it's like a kill switch type. When, let's say, you are out of range, and we have this RF joystick, which, let's say, for example, you're out of range, you do not have access to the Wi-Fi, then we will be using at that time this RF joystick. Now, how it's going to work? So, already Vishwa covered this, the Arduino sensor. So, we are using Android sensor. So, we are using Android phone as a sensor, where we are getting this all motion sensor as well as the GPS. Now, this part is already covered. I'm going to talk about how we are going to communicate and talk with the stepper motor and the BLDC motor through Raspberry Pi over ROS. So before getting into it, we need to understand that what generally they understand, the language, the communication protocol. These things are important before getting into the straightaway integration. So for example, let's take the first example of BLDC motor. So BLDC motor, what it accepts as high and low level logic as a control signal. It has like three phase. It's a 3-phase BLDC motor actually. So this drive understands the low and high level logic. Accordingly, it converts that command to the BLDC motor on a 3-phase wire. And then there will be a Hall sensor in the motor which will be giving you the feedback, and then the drive will understand that when to shift the phase of this motor. So this is how it communicates. Now, how will generate the high and low level logic is the question, because this is what the communication it understands.
What is a Hall sensor?
So Hall sensor detects the induced EMF. Like if we have coil and we put those sensors there, and then it detects that okay, do we have this magnetic field there? Because of change in the electric field, we get the magnetic field there. So it detects and then it tells that okay, now this coil is activated, and these are like not activated. So the torque corresponding to this, like we have Hall sensor A, B, and C.
Okay.
So there will be 3 Hall sensors. I'll show you this where it is that it's written. So it has the 3 feedback coming from the motor. So it's mounted on the coil. It gives you the position of where the actual your rotor is.
The Hall sensor basically tells me what is my position of the shaft.
Right.
It kind of encodes the position of the shaft.
Yes, but the problem is it is once the drive understands that and it generates the signal accordingly. So when we say that we are generating PWM, it's going straight away. No, it won't do that way. What it does, it converts in a, let's say, trapezoidal form or sinusoidal form, whatever it understands. So for example, if this motor is sensorless, we do not have sensor. Still it's a BLDC motor, but what we do is we take the input, we define the input, like on the PWM, the ESC, those are called electronic speed controller, the small ones. What it does is, it takes that input as a PWM, but it converts that into trapezoidal form. So and then accordingly it runs. But here we have feedback and we need it. Why we need it is because we are not running at high RPM. Let's say for example our thing is like low RPM and high torque. So
we are not providing 3-phase current to the motor.
No,
We are providing a direct DC voltage to the motor.
Right, sir.
Right?
Yes.
So the drive is making it into a 3-phase current system.
Yes.
Such that one rotor after the other, one coil after the other electromagnetic coils are getting activated so that the motor rotates continuously.
Yes, sir.
Okay. So in a BLDC motor, is there a permanent magnet?
Yes, we have permanent magnet.
Is that a static or is that the rotor?
That one is the rotor. That's when it will be rotating, and then those coils will be static. So that will be changing, and then your permanent magnet will be moving.
Correct. So unlike in a regular motor where you have the static part is the fixed magnets and the coil is the rotor is the one which is the coil. Here it is the opposite, where the static is the rotor and it is the coils which are driving the motor. So 3 different coils which are connected in different. So each of these 3 coils are activated at different times.
Yes.
In order to rotate the motor.
So the permanent magnet has this north and south pole, and then it will the electrode the windings. We call it as a winding. So the winding will induce that magnetic field because of changing the electric field. It will induce that magnetic field, and then this guy will repel, and other side it will attract. So that's how it will keep shifting.
So those 3 phases are really important for the motor to keep running.
Yes.
Okay. I think did everybody get that? Yes, no?
Yes, sir.
Okay. If not, please ask. Okay, don't feel shy. If you feel shy, then we will never learn. The whole point of this exercise is to ask as many questions which come into your mind whenever they come. All right.
Okay. So, and then similarly we have this stepper motor. So this also understands the pulse form, so high-low level logic, and accordingly we generate it from using the command. We generate it through the controller. Now, why we are using the controller? It's because I'll first talk about what the difference between the microcontroller and the processor. Then probably we'll be able to understand more that why we are using a controller there. So if we have a microprocessor, so these microprocessors are generally, they do not have any GPIO pins. So if they do not, what they generally do is they have a high computational power. They need more energy. I mean, the power requirement is also high. They can do, this ample of computations. So, for example, let's say if you want to do some sort of inverse of a matrix, which is like, let's say, very huge, let's say 6 by 6 or 8 by 8. Probably, if you implement the code in the microcontroller, there are chances that it will go out of range and it won't be able to do the computation. But here we have the microprocessor which does all that. So why we are using the embedded system, the controller? So controllers, they do a specific job. For example, you just code it and forget. Whenever you switch it on, it will do that specific job, nothing else. For example, let's say sequential, you have a washing machine which does sequential stuff. So you just program it in that way and it will do the job. Also, it has a very limited, RAM capability and the ROM capability. So these microcontrollers are for less computational power and they do a specific job. Like we have these embedded devices, which are like, as I said, washing machine, or let's say you have a robot which does only that line following. Let's say we have a line follower bot. So you can code this Arduino Uno and it will do every time the same thing. But let's say if you want to do certain feedback and then you want to take decision on the go, then you have to use this microprocessors to do this computation. Now, so how when I said that we need to communicate between these peripherals, so we need to understand that what exactly those peripherals are, right? So for example, here we have the CPU and we have the microcontroller. So for this, we need inter-system protocol. It means like I'm communicating between processor and microcontroller. So for this, we have these protocols like UART, USART. They are like, most of them are like serial protocols. One is synchronous, one is asynchronous, and then we have this USB protocol. Now, examples are Pi, between the Pi and Android, Pi and Arduino. So yeah. So as like you'll be remembering Vishwa when he was telling that we have this accessory mode and the host mode. So for example, if you are going in a host mode, you are communicating between a processor and the controller. But when you are in accessory mode, now this becomes your accessory, your Android device, and your computer become host. So this is how we communicate over, and these are the protocols we need to use for that.
No, but that is kind of a little confusing, isn't it? Because when you connect a Arduino to a Raspberry Pi, they're both processors. Arduino microprocessors. None of them is a microcontroller there. Isn't that right?
No, in the Android level.
When you connect the Android to the Pi.
Yes, sir. So what happens, that's why those protocols are there inbuilt, like as he said, accessory mode and host mode.
Correct.
So there we have to predefine that how we are going to use that device.
Okay.
So for example, if you want to access the ROM of your device, the Android device. So what you will do, you will simply connect and you will be accessing the ROM of that device using this protocol. Okay. Now, if let's say I'm using the Android and Arduino board. So in that case also we can do that over, but then also we have to use the USB protocol.
How is it different then?
So yes sir, that's one. So for example, I'm not using the OS of the system there.
Okay.
In the let's say for example, when I'm communicating between the computer and the Android. Okay, let's say for example, you simply connect and do file transfer, you do whatever those things. So we'll be accessing the part of the ROM there. Now, but if we want to use the code, I mean the inbuilt functions of your Android device, like how Vishwa did, you have to tell that in which mode you are going to use it. And but let's say for example, if I'll directly connect an Android to Arduino, then what will happen? It will detect that guy as a microcontroller, Arduino. That is like a microcontroller. And your this one will be like your microprocessor.
The communication protocol is simple.
Simple.
Because
Yes.
one is the host,
Right.
the processor will be the host, the controller will be the
Right. Yes. So that's where like when we started doing this one, it was like we thought of first go with the Android and Arduino and then communicate. As you remember, we were telling that we will use the RS-232 communication and all. Because we found that accessory mode is a bit tricky but Vishwa did that one. So now another protocol we need to understand is, for example, you people would have heard of this MPU 6050 or 9250. These are like IMU ICs, which are like cheap ICs. So when we communicate between a controller and IC, so we need these protocols like I2C, SPI, or CAN protocol. So for example, there are few motors which only work on CAN protocol because they do have the inbuilt drive which we are using, like you can see the big drives here. So if you go with the Maxim motor, they will be having this CAN protocol inbuilt. So it means that you can control those motors straight away with the microcontroller over this CAN protocol. If you want to go with the chip-to-chip communication, you need to use either I2C or SPI protocol. So these are like what do you say that dedicated protocol.
What do these protocols in essence mean? Like if you wanted to dumb it down, what do these protocols mean?
So for example, we let's say we have one integrated chip, which is like of flip-flops or let's say transistors or diodes or whatever. Those will be there in your chip integrated. Now there will be a small controller also which process the those values. Let's say those analog values will be converted into useful information. Now how we will access those which are there on the chip, okay, through the microcontroller. Okay, so microcontroller again is a chip which has all this logic gates and diodes and transistors, whatever they have inbuilt integrated in that one. So now if we want to communicate between these two, our understanding should be in that way that both should understand the same language. Now let's say for example with the I2C or SPI protocol, what happens? So I have a IMU which is like a chip, and I'm going to integrate this with a microcontroller Arduino. So what I need is I need the address bus, I need the data bus, but on top of it I need to have that clock. So this SPI works on that protocol. So where you have synchronized data transfer. And let's say for example, if we have the integration, this IC, which is like for example, as I said, the Maxim motor. So what they do is they have the motor, they have the integrated drive, they process everything in that integrated drive, and then they are giving us the CAN protocol to use. It means it's up to manufacturer. For example, if we are buying any sensor, what we will do is we will ask them, can you give us the serial interface? Can you give us the SPI interface or I2C interface? And while manufacturing those sensors, they will come up with that, okay, I'm giving you this.
So when you are programming, so you can think of these as languages in essence. Languages of communication between the multiple.
Communication, right, yes.
Multiple between an IC and between a microcontroller and a chip.
Yes.
Right?
Yes.
So the idea now becomes that in your microcontroller, we program to communicate in multiple protocols at once.
Yes. So it all depends at what microcontroller we are using. So for example, we have a basic microcontroller which has only only SPI protocol, which has both also, and which has like UART as well. So it can do over serial communication as well. So this is microcontroller. So microcontroller comes with all this communication protocols. But our integrated ICs which are there, which they have very minimum functionality, which are not like a development board, So it will be like what do you say? It's like converting this. So yeah, so it will be like if you have IC which is like of minimum capability, like I'm just taking the analog voltage, reading it and converting it into some voltage, some useful information. It can be either serial, string format, or. So to understand these protocols, we have to go to the machine language. So let's say what happens is we have the address bus, we have data bus. So address bus, what it does. So all these integrated chips, they have this memory. So you want to access those memory. So you need the address of that memory where you want to go. So it goes to that level. Whereas these protocols, they do all this behind the screen, but what will be happening, what they give to user is like more of like high level language. So this is the difference between these two protocols.
One is like having to install a driver on a operating system to connect to your printer. The other is to have a plug and play protocol.
Yes.
All right.
Okay. So yeah. So these are the things, basic. For example, also as I said that when you are going to buy something, either sensor or motor or whatever, you need to understand that first what your controller is, what your processor is, what you are using, and what it understands. What all protocols are available on those PI board or let's say controller board, and then accordingly you fetch the motor or the sensor. Like for example, if I'll go ahead with a RTC, which is real-time clock, and let's say I do not have I2C communication on my processor board, then I cannot do it. So for example, right now I just want to give this example because I'm using it. What I'm using right now is a micro PC, a straight away PC on a chip model. Now, if I want to communicate between the I2C, between the real-time clock or MPU 65050, I cannot do that. I need something in between. But if I have a Raspberry Pi, I have all this as a GPIO. I have I2C, I have SPI, all those communication protocols are there. I can straight away communicate between those.
So these are GPIO pins on the Raspberry Pi.
Yes.
You can actually give out these different protocols like I2C. Certain pins can communicate on I2C, certain pins can communicate on SPI, or some other protocols.
Yes.
Okay. All right.
Okay. So yes. So let's go ahead and start with our BLDC motor, how we are going to control with the Raspberry Pi board.
Maybe before we start on that, one big question.
Yes.
So when you look at an Arduino, the regular Arduino board which we are using right now, what sort of protocols can it handle? It can handle I2C?
Yes, it can handle I2C.
It can handle SPI?
SPI, I'm not sure. I think no.
Okay.
Yes.
But
I have to check. Yes.
So
I2C.
your IMU, which you generally use on as an integrated chip, which those communicate on which protocols, general ones which are available commercially.
That I2C and SPI. These both are like common.
They are both commonly communicating on I2C or SPI.
Yes.
Okay. So if it is on SPI, then it becomes a little tricky to control it with Arduino because if SPI is not available.
Right. Yes. So then we have to look for some other controller board like Arduino Mega. You can look. Or let's say I'm just assuming that it's not there. I have to check. Let's say if it is not there, then I'm sure that in Arduino Mega it is there. We can go for
Arduino Mega rather than the regular Arduino in order to use the SPI protocols to communicate with our sensor in that sense.
Yes.
Oh, all right.
So yes. So this is like what I was talking about, the BLDC motor, what is all how we are going to communicate and how we are going to.
1 second. Any questions so far? I think now is a good time because once he starts talking about BLDC with pi, once he starts talking about BLDC with pi, you will not be able to ask so many basic questions. If any other basic questions are coming in your mind, now is a good time to put them out. If anything was not clear, you can ask, and he'll be happy to repeat a little bit as well. Am I audible?
Yes, sir. So like first we have the Android, the Android has all the sensors. It is communicating to the Raspberry Pi, and Raspberry Pi is to the these two microcontrollers, say that you showed in the first slide, and the protocol between Pi and these microcontrollers. That's what you were saying, talking about, right?
Yes.
Actually, both ways. One is between the Pi and the Arduino, and also between the Arduino and to the integrated chip, which in this case would be the drive,
Yes.
right?
So, but here, yeah, its drive is like a high level because they have processed everything and they're giving us this high level and low level thing and stuff. But in case, like I gave this example of another IMU, which is like integrated chip, a small one. So if you search MPU 6050 or 9250, you'll be seeing that it's like a integrated chip.
So what he's trying to say is that generally, in our case, we are using the mobile phone as a sensor suite, right? But inside the mobile phone also, there will be all these different sensors. For example, if you look at Google Pixel phone, it will have a watch IME inside of it, which is mounted on an integrated chip. Similarly, he's talking about one IMU which you can directly buy, and it is used in robotics applications where you mount it on an indoor robot and it can give you the accelerometer data. When you want to communicate with such chips at a low level interface, unlike through the smartphone, which is a higher level interface through the USB, you will need to follow these protocols. Am I right?
Yes.
Did that answer your question, Mallan?
Yes, sir.
Any other questions? Good question.
The in the picture, in this particular picture, the lower the Arduino that is shown, the lower one, it's connected to the one that sir mentioned, right? Like the onboard sensor type.
Which one? Sorry.
This lower Arduino picture that is shown,
Yes, yes.
the one that is not connected to the Raspberry Pi. The
No. So this is like it communicates with RF joystick. So as I
Okay,
said,
okay.
if you are out of range, we have a dedicated system which controls your both motors, the BLDC and the stepper. So
Okay.
I want to cut the Raspberry Pi and I will completely switch to the RF manual control and where we can access through joystick.
So you can think of this as a manner that, let's say that you are trying to run a turning circle experiment on your graph, which means you want to hold the rudder at a certain position and you want to execute a turn. And you observe that, oh my God, there is a tree in between into which my ship is going to run into. So you want to now stop the experiment and take over a control of the boat, isn't it? Right? You don't want to crash into the shore or into the lake or into the obstacle which is there. Am I right?
Yes, sir.
So in that case, you want to take over a manual control of the vehicle. And what you will affect through what is called a radio frequency based control. That has to be independent of your onboard system.
Okay, so we will actually have two different Arduinos. Like the one will only communicate with Raspberry, and one will only connected to the our controller in our hand.
Correct. So one Arduino will be connecting to our radio frequency based receiver, which is whose transmitter will be from the base station. This joystick type of thing which you see is going to communicate with this guy right here.
Yeah.
Okay, and when I flip a switch there, what should happen is this Arduino will be in command rather than whatever commands which are coming from the other direction will be disregarded. Okay, so then you take over panel control and you essentially have stopped the experiment and you're making sure that the vehicle doesn't come to a harm.
Yes, sir.
All right, any other queries?
Hello, sir.
Yes, Aditya.
Sir, is it possible to use just one Arduino instead of two?
No. So the point here is, let's say for example, if your system fails, which system, let's say if the Pi hangs or whatever happens, I want a complete dedicated control for the manual. For the manual control to these motors. So this Arduino, what it does is it does only a specific job of generating the PWM and the high-low level logic. No computation, no OS running, nothing. It's very simple. Whereas if this one is connected to the Raspberry Pi, and even you can use these pins which are there, but the point of having a dedicated manual control will be then it won't be there then, because if this Raspberry Pi fails, you're doomed. You cannot access this Arduino board.
And also you don't want some signals from the Raspberry Pi to be messing up your control, if at all, if they may interact. You want to avoid that possibility altogether by keeping the two systems separate. It's because it's a kill switch, right? And whenever you want to go into a kill switch module, you want to kind of keep a redundancy there. So that's the primary idea, how I look at it. It's not that you can't use it, but then you are kind of saying that the Raspberry Pi becomes my Arduino becomes my bottleneck. Is that making sense?
Yes, sir. Yes.
Okay.
Sir, just one question. Like when we are switching to this manual mode, is there some way in which the other Arduino knows that this is going into manual mode, because there is no connection between both the Arduinos, right? This is just separately connected to the relay over here. So
good question. Yes, sir.
yeah.
So what we are asking is, if we are switching, whether the other Arduino will be knowing that we already switched to it.
Yeah, because that will be sending signals, I believe, right, continuously. So
So of course it's not there at the time. For the time being, it's not there. At current time, I didn't code that way. But I think it could be done, because what we are doing is, generally how it works is, I'll tell you. So we have this joystick here, which has the switches, right?
yeah.
So if you flip one switch, what happens? This relay will switch. So this relay will be having this normally closed, normally open type of pins. Okay.
Yes.
So what happens when you flip that switch? The relay will switch to this controller. Okay.
Okay.
Whatever control will be coming from this joystick will be then given to this controller, and this controller will process the command, and then it will go through the stepper mode. Now our BLDC motor. So the common of this relay will be connected to this motor, right?
Got it.
Okay. So what we are doing is, we are just switching the control signal of this stepper and BLDC, okay, using this relay.
Relay. Okay. Got it.
and this relay is switched on. So, but as you said that if other guy is not doing, I don't know why it is important, but let's say even if it is important, we can do that because we have one channel which is just switching the relay, okay, and we got some logic, low level or high level logic by switching it. We can pass it to the other Arduino and we'll say that okay, now you stop, you don't have to further process any data. So I think it can be.
But I think it's better not to do it.
Okay.
Because let us that kind of makes your redundancy go away. You don't want this Arduino to be communicating with the other Arduino at any point of time. Preferable. Because or even if it communicates, you don't want to rely on that connection. That's the whole point of the redundancy, isn't it? It is best to do it in a way where you have done it right now through the relay, where you're simply disregarding whatever that fellow is publishing. Because let us say you pass on the signal that don't send a signal out. But suppose that fellow malfunctions and continues to send a signal out and you are relying on the fact that I have asked him to stop, so I expect him to stop. But he may not stop.
Yeah, but even whatever it does, the thing is that our full control is shifted to this controller.
So the relay is the key.
Yes.
So once relay is there, which is switching the control,
Yeah.
it's really not needed to ask the other person to stop publishing their commands.
Okay.
Am I right? Am I missing something or am I okay?
Yeah, that's why I said that probably I don't know whether it's important, but yeah. But I think it's important to have some sort of indicator that now we switch to RF mode. I think that because let's say for example you put an indicator on the ship model, and then when you flip the switch, there will be like some indicator on the ship which should say that now you're in RF mode.
Yeah, but why does the Raspberry Pi side of it needs to know that? Or what
No,
will
not
it do
that
with
that
that
is not. It
information?
is only for the user. It is only for the user. Because sometimes what happens that you have a joystick switches and you'll get confused. Oh, whether it is I'm in RF mode or off. So
In that.
sense.
Okay. So there may be a point. Okay.
Sir, but I just have one question. If we do it in that way, the thing is, we are not telling the whole the autonomous system which we have built on the Raspberry Pi. We are not telling that right now it's in manual mode. But then when we switch back to the autonomous mode again, it will start from after some
Wherever
delay.
you are.
Right?
Correct.
Yeah. So,
Continue to execute the same commands what we had previously given it.
yes, sir. But then there might be some issue. I'm just guessing. I don't know when we implemented this may come up, but I'm just thinking of this. That what might happen is that let's say the control system which is running on the autonomy part, and then when we try to do it in the manual mode, it just drifts away from the target, and then the whole autonomous system is still stuck on the previous target, right? So.
No, my point is the moment I have switched on the RF mode,
Okay.
I will start the experiment altogether.
Right.
Okay.
There is no way I am going to go back to it again.
Okay.
It is a kill switch, which means that things have gone really haywire.
Okay.
There is no point of return. It's at a point of no return.
Okay. Got it. Okay.
Okay, let's move forward.
Okay. So yeah, this is how we are going to do this now. Control of the BLDC with the Raspberry Pi. So as I said, the BLDC is three-phase motor. It has a three-phase, and then it has the drive, okay, which understands that what is coming feedback as a feedback from the hall sensor, which is mounted on the motor, and then it understands that and generates the phase shift in the 3-wire, and then accordingly the motor moves. Now what the drive pins which are accessible to the Arduino or the Pi board is this 4 pins. So enable, brake, direction and speed. So this enable, it understands only high and low. break also it's high and low because these are our digital pins. We have a direction which again understands high and low. And then we have a speed which understands analog or PWM. Now, with the high and low, it's quite easy to do because you always have this digital I/O pins on your Arduino or on your Raspberry Pi. But this analog pin is generally not there because why it is not there? To do that, you need digital to analog converter. Okay, which generally these Arduino boards they do not have. So what we are using is PWM. This is another alternative to generate the analog signal, but of course it won't be that accurate what analog signal will be as compared to this PWM. But yes, using that PWM duty cycle, we will be generating the corresponding analog voltage in some sense. So our drive they come with a switch where you can either do the analog or you can have the PWM. So right now we are in a PWM mode because our Arduino doesn't have the analog signal. It does not have the digital to analog converter, but it does have this one analog to digital converter. So you have analog input pins on your Arduino or any Arduino board. Now, yes, I was telling that we are using Arduino in between because this to just avoid the clock cycle of the main computer, just to be getting wasted in just generating the PWM for the stepper or the BLDC motor. So how it works is from Raspberry Pi you send some command and you forget about it. The Arduino will take care of it. It will be just generating. It will keep doing that work only, generating the PWM and for both the stepper and the BLDC motor. So in that sense, we save a lot of clock cycle of our processor. Even we can straight away connect to the Raspberry Pi board, but it is not advisable.
When we are looking at the input for the Arduino, you talked about the idea that it has analog inputs as well.
Yes.
Right?
Yes.
Are we using them in this one? No. We are using the PWM over the RF as well.
Yes. So it has analog input, but to control our drive, we need analog out pins. So to get that analog out pins, you need digital to analog converter. It's an IC. But it has this analog to digital converter. So you have any analog voltage. Let's say, for example, you want to read your battery voltage. Up to 12 volt and TV allowed. So if you want to read your analog voltage from the battery, it will you can just plug it to the analog input of your Arduino pin, and then you quantized and sampled it, and then you will convert it into the digital form. So it will give you some digital value corresponding to that. So this is how it works. But we are not using right now the analog input.
We are only using pulse width modulation.
Yes.
Is everybody aware about what is PWM? I know electronics background guys know it thoroughly in and out, but I'm not sure whether all naval architects will necessarily know what PWM stands for. Everybody is familiar with PWM?
Yeah, it's like square waves, and we can change the size of the duration of how much time it is on and how much time it is off.
Correct. So if you are applying a 5-volt signal for 60% of a duty cycle, then that is equivalent in an analog sense to 3 volts. You can think of it like that.
All right. So what this is the architecture which will look like what I did for the communicating with the Pi to Arduino and to the drive of the BLDC motor. So from Pi, I will be running a ROS code here on the Pi. Okay, we have a ROS publisher node running, subscriber node running on the Arduino, and we have a publisher node on the Pi board. And these two, Pi and Arduino, it communicates over serial. Now, what I'll be doing is I'll be sending these commands: forward, reverse, then speed, and then start, stop. So S for start and X for. So this I will again decode in Arduino, and accordingly I will take action on my digital I/O pins. Now this digital I/O pins will go through the relay, as we discussed, and then it will go to the drive and then to the BLDC motor. And this is for the RF receiver, because BLDC is again, communicating with the RF joystick as well. So this is for that one. So here we will be having a pi only as a processor. Why? Because let's say, for example, you want to develop some control logic. What you will do is, we will be getting the sensor data from the Android phone. You take that, you design your control, you take feedback, whatever you want to do, you do in PyBoard, and just only send the actuator signals to the Arduino board in terms of whatever, the speed, forward, reverse, or start stop. So let's say, for example, you want to do some sort of bang control, you want to go forward with a full speed and stop, you just put the speed value and start stop. That's it. So you don't have to do any computation on your Arduino board. So this is the whole idea about it.
So it's like a slave which is doing whatever it is being told.
Yes. Okay. So similar way, we are doing this for the stepper motor as well. Okay. So again, the same thing. We have the drive. We have the stepper motor. So I'll show you how these drives look like. We have it here. And again, this have this pulse positive, negative direction, then enable. So this enable is to enable the motor drive, and then you have direction. You want to go clockwise, anti-clockwise, and then this is pulse for what angle you want to make with your stepper motor. Okay, and the same architecture we are using the Arduino. So pi will be sending commands like you say this much decrease, and then you say that clockwise or anti-clockwise. That's it. It will do the job. Yeah. So and this is pi and the Arduino interface. So how these two are communicating? They are communicating over serial, and ROS libraries are used because this both has to communicate over ROS. And yeah, there will be publisher running on the Pi and then subscriber running on the Arduino board, which will be subscribed to the Pi node in the Raspberry Pi. I mean the publisher node. And yeah, and we are forming the mission string. So for example, if you want to do some sort of autonomous control completely, you can form a mission. Let's say you want to do a path following, you form a mission of, let's say, waypoints, and then you say that path following, and you just jump it. So this is where the mission string will be useful when we will be doing this for the further advancement.
So what will that mission? So probably we have
here right now it's in open loop. So here the mission will be very simple. You go forward with this speed, and with this steering angle, you just
so there's no feedback here.
no feedback.
Okay. But at a later point you can get the feedback which you are getting through the sensors. You can use that
Right.
to
Yes.
modify your mission.
So what Vishwa has done, we will use those, and he has already put as a publisher node in the ROS. So we'll be writing another ROS node for subscribing to those topics. It will be, let's say, it will be a control node where we will do all sort of algorithm this one because we need the sensor data, and then we will again publish that one to the
Arduino separate. Yes. So Arduino will be now reading on the topics based on the correction and the original mission.
yes.
So I'm thinking of this more in line of, let's say that I ask it to follow from one waypoint to another waypoint. Okay. The simplest task is to follow in a straight line and get there. But now the sensors detect that there is an obstacle which is coming in between, right?
Yes.
Then the object box, the vehicle has to take a deviation so as to avoid the obstacle, and then after it has crossed over the obstacle, it has to come back to the path that it wants to reach, or it has to kind of try to reach its destination waypoint. Right? So in that sense, there will be a separate node is what you're trying to tell, which will tell that, okay, yes, this mission is now more important. Obstacle avoidance is more important as compared to your path following in the current scenario. In some way that will be encoded.
Yes. So the point here is we will be having all the sensor information. Let's say we have a sensor node. We call it as a sensor node. All sensor node values will be, let's say, coming in that one. And then you have separate algorithms, control nodes. Okay, so let's say you have a control node for obstacle avoidance, you have a control node for path following, and all like that. And then we will be having another one where we will merge it based on our whatever we want in the field. Let's say, of course, the collision avoidance will be the prior task to do. So accordingly we do, and only actuator signal which will be coming out of this, let's say turn, because the stepper will turn now. So that actuator signal will go to Arduino board. So Arduino board will be always having only one subscriber, which will be subscribed to the control action. So that control action will be in form of rudder and the speed and all those stuff.
Yeah. And that logic of what is happening or how the autonomy is coming through is going to happen on the pipe.
Yes.
And that pipe node, after it has gone through this process, will be generating the signal and giving Arduino as to what to do. So I am thinking, what does the Arduino get right now? Like, I want so and so speed and so direction.
Yes.
That is what it kind of gets the information.
Right now, it's the rudder deflection, not even the direction. So let's say, for example, rudder deflection and the speed of your motor forward.
It's the RPM of your forward speed.
So that we have to decode, because generally people won't be inputting the RPM of the motor. It will be more like at what speed your vehicle should go.
Correct, but that is not what the Arduino will do. So the Arduino will try to decode from it.
Correct, sir. So what we will do is, let's say for example, we got some constant value after calibrating that, okay, your speed of your vehicle moves at 1 meter per second at that particular RPM. Okay, so we have a function which relates the RPM and the speed.
I think it's better to keep it separate. You keep the rather than asking to provide the Arduino with the speed of the vehicle, it is probably better to provide with a commanded RPM. That is always better. You can always feedback the sensor information to make sure that it matches the required speed. See, I'll give you a very simple example. So let us say that you are going in a straight line.
Right.
Okay. Then the amount of torque which you are applying or the amount of thrust which you are generating at a particular RPM will be sufficient to match the speed. So for example, let's say our KCS ship only, if we consider it full scale, 1.94 RPS revolutions per second will roughly allow you to go at 0.26 root number. Okay. But while you are executing a turn, even though your RPM is still held at 1.94, your speed decreases by 40%. Right? So vehicle speed is different in both cases, but the RPM reads the same. It is better to publish the RPM directly and ask the Arduino to match that RPM. You calibrate only the RPM of the motor and let the hydrodynamics be a separate portion of it itself.
No, okay. So no, here anyway, it was all open loop. I mean, I was telling that it will be like generally how we do here.
It's better not to do it, is what I'm saying. It's better to encode rather than speed of the vehicle, encode the RPM which you want to achieve.
Okay.
So what you publish from the pi to the Arduino should be the RPM of the prime mover, which is the BLDC motor, and what is the angle at which you want to hold the rudder. Commanded rudder angle, commanded RPM. Those are better to have at hand rather than the speed, because once you talk about speed, you are kind of throwing away a whole lot of physics of the hydrodynamics out of the window there. And you are saying that I'm open loop calculating it. It may not be the valid for different situations. But that can be taken up as a part of your control law, where it is looking at that, hey, my speed has dropped.
Yes, and I want to maintain.
Now I want to maintain the same speed. That may be a part of your control logic on the pipe. Need not be given or offloaded to the controller.
Yes.
Okay. All right. Any other thoughts, comments?
So now we can go ahead.
Yeah, now let's try to go ahead and see this in action a little bit.
Yes.
Yes. All right. I know you'll have a tough time typing over there.
Okay. Okay.
But please walk through what you're doing so that,
Can you stop sharing this screen?
yes, can you stop sharing the screen so that that screen is visible?
Yes. Okay.
All right.
So first, we are in here. We are right now in Raspberry Pi, and our ROS core is running here. So I'm also beginner. I'm very much beginner in ROS. So whatever I've done, it's all basic. Okay. So here we have.
Sir, the focus of the phone is a little, or is it my connection?
No, it's the same for me also. I think maybe the send resolution could be set to high, so it could be better. Now it's better, I think. Yeah.
Okay, so what we can do is, I think I have understood. You increase the font, Awanish. That will do the trick.
Okay.
You increase the font here. Okay. Okay, it's okay. It's not too bad.
Okay. So before starting, as I said, it need to communicate with your Android Arduino. So Arduino, we have to communicate over serial, and to run that serial, we have to run this command somewhere.
Okay, maybe what we can do is we can close everything,
No, here it is. Huh?
restart. Not close, like stop all the nodes,
Okay.
restart all the ROS code, restart,
Okay.
so that it kind of leads to a continuation of how it is being done.
Okay. So let me do this. Yes.
Your system has done.
This is the best part of Ubuntu. I never liked it. Sorry, just a second.
You have to change your password after this, okay?
Not required service. Anyway, it's search PC. No, I think I need to reboot my system.
Okay, do it. Close the terminals, no?
It's not happening.
Just X. Kill.
No.
Yes.
Yeah.
Alright.
Okay. I got it. How it was happening with this. My bad. Anyways,
Because you're connected to CCON, why not to this?
yeah, it's automatically got connected, I think. Okay. Anyway, so
Yeah, maybe you want to push this back. You from this guy here, so that I watch the screen and make sure that it's happening right now. I think.
okay, so here what we have is Raspberry Pi. What I did is I made this as a server where we can straight away connect it. Now let's get
Now, before you do anything, increase the font to times. Okay. Plus another one. Again, go back. Another one. Now, okay, are you able to see this a little bit?
Yes, sir.
Yes, sir.
Okay.
So we are getting into now Raspberry Pi. Okay. Now we are going to go. Now we need to source.
For my benefit.
Yes, sir.
Forget about this. Take the laptop into your hand. Sit down. Is this better, guys?
Yes, sir.
All right. So this command basically helps you source the ROS into your system. Now he's starting a ROS core on this.
Already it's running.
Yeah. So there is a ROS core already running on it. Now he's sourcing the files which he has written, or the controller files for controlling the stepper motor and the BLDC motor. He's sourcing those files so that they are now available. Because he opened a new terminal, he has to again source all the code again. Now he wants to run his code. So he's using ROS run.
To do that. Okay, that's right.
Okay. We'll either die of suffocation today or we'll be able to redeem this.
Okay. So now this is what we established the communication between Raspberry Pi and Arduino board. Now we'll go to our code and we'll run. So now this code is running on the Pi board, and it's asking for the user to enter that into the command for the BLDC motor. So let's say forward, F for forward, R for reverse, and then you start the motor, and then you give your speed. So it's right now I'm just giving the duty cycle because I didn't calibrated it yet. I didn't calibrate it yet. So then we have the direction. You give the direction, 1 for clockwise, -1 for anti-clockwise. And then you put the number of steps. So here I have encoded with this degrees. So when I say 90 degree, it will go to 90 degree.
And the stepper?
Yes. So both will run now. So
No, wait. Okay, so right now the first 3 commands are for the BLDC.
BLDC. Right.
And the last 2 commands are for the stepper.
Yes.
Alright, so we'll take one at a look. I'll not be able to cover both the motors in one shot.
I think now we have.
Okay, so this is the stepper. The moment he does that, it will rotate to 90 degrees. Did you guys see that?
Yes, sir.
The there on the front has moved to the side. If you look at the side now, you will see the tape over there. And what's happening with the BLDC motor is it is rotating. And you can see that from the tape, how many cycles it's going. It's rotating at 70 RPM.
It's 70 duty cycle.
70 duty cycle, 70% duty cycle.
70%. Right.
Okay, so now we come back here.
Yeah.
And you will say reverse, and then it will reverse and start here. And speed 70, the same.
And then you want to rotate anti-clockwise, and then with the 90 degree again, it will come back.
So which means now once he does that, you'll see that the stepper will come back. So you see the stepper came back. And the motor continues to now rotate the other way around. Okay. So we have now seen a demo of this. What I think will be curious. Okay, he's now trying to stop the motor. And now the motor has stopped. So if you look at his commands, he has given X for the start and the stop,
Yes.
and nothing else for the rest.
Right.
And that has just simply stopped the BLDC motor. Okay. Somebody was trying to ask a question in the meantime when I was trying to do this hula hooping. Shadab, was that you? Were you trying to ask a question?
No, sir.
Okay. All right. Okay, so now what would be of more curiosity is to look at the code. Okay, now that we have at least kind of they have seen what is happening, what you can do is you can join from here and share your screen. That way we can see it a little bit more clearly. And I can neatly shut off the video here.
Sir, I have a question, sir. Hello. Hello.
Are we audible?
Yes, sir.
Okay. Yeah. So, okay. So this is how it code like. This is the basic structure how we use the ROS, and then this ROS node handle where it handles the communication between the Pi and Arduino and Arduino. Yes,
You're writing this in C++.
it's an Arduino language also.
Oh, okay.
Yes. So and then okay, so this is the Arduino code. I think most of you will be aware of that. We have these pins, digital I/O pins we have, but I have put for pulse, then direction, and the enables. This is for the stepper motor. Then
So those are the pins which you're trying to access from the Arduino.
yes, sir. Right. So this pin will be directly accessible from this code to the Arduino because that are the GPIOs of the Arduino code. Now we have other one is for the direction, for the start stop, and this is how we are getting the speed and the rudder angle. So what I'm doing here through this code is I'm getting the data from the Raspberry Pi from the Pi publisher node where I have subscribed. So if you see here, so I have subscribed to this topic autonomous of ASV, okay, and then I'm getting when I'm getting this strings which I'm formulating in terms of a mission there, okay. So what I'm doing is I'm reading those characters, okay, and then accordingly I'm taking the what you say the decision which I'm trying to make it here. So let's say for example, so this is my stepper motor function which takes the int value of the direction and the steps, and then I have this where I'm getting this data in terms of a string. So here you see I'm doing this, I'm taking this as a speed value, direction, then I have this break is belongs to a start stop. Then we have the step direction, it means the stepper direction, and we have the step number, it means that the angle which at what angle you want to go. Now once you have these values, you decode it. So let's say for example the direction, so direction is like here. So if direction is forward, you simply make that the 7th pin which is assigned for the direction of a BLDC motor which is connected to the drive, as I said, as I was showing in the drive pins. So the drive pin was having this direction pin, so this goes to the 7th pin is connected to there, and then you are just making low and high. So what you're doing by making this low and high is you're just putting 5 or 0. So high for 5, low for 0. So and then it does the job because that's what the drive understands. Similar way we have this for the brake, we have a start, we have a stop for X. So again I'm making this low and high. Now the values which we are entering in terms of the speed, as I said that is speed, and later we have to change it to RPM. So here I am doing this. So it's just what you're doing is you're getting that value, converting into the inform, and then giving it to the PWM signal. So here you see it's a simple inbuilt function in the Arduino board where you just simply say analog write, and then you say the RPM value, whatever the RPM value it will be. So it will be doing the job. So yeah, and then you keep running. So this is where where you can set your baud rate. For example, this generally the serial communication, they have this baud rate settings which says that at what data rate it's I mean, indirectly it says that data rate, but generally it means that you have a symbol change per second, or what are the symbols changing. Like for example, if you're sending a string, so if it is high baud rate, it means what we'll be doing is your data rate effectively will be high, but at the same time your length of transmission will decrease. So you cannot use high baud rate for long transmission. I mean, but in our case, our model is like 2 meters, and then we have placed this close to the Raspberry Pi, so we don't have to bother. So we are using the maximum baud rate which is available with the Uno board. And then let's say this is our loop which runs, and I have put a small delay there, 100 milliseconds. So because it doesn't matter that when we put this delay, it doesn't matter much, because anyways our job to do is only to generate a PWM signal for the BLDC motor. So and
pin 13?
Pin 13 is another high-low pin, digital I/O pin, where the LED is connected on the Arduino board. So it's just to check that your program is working well or not. You receive something and then you want to check whether it made it high or low. So your LED will go blink, and then
so it's kind of checking.
Checking and verifying. Yes.
Okay. Okay, so I think what would be more interesting is, let's look at some of the test cases which we tried out.
Mm-hmm.
So when we gave the stepper as 90 steps to turn,
yes,
and you wanted it to turn in a clockwise
right.
Where would what would be the piece of the code which would be relevant for those commands?
Yes, right. Okay. So as we receive this string, so we will be here. Now let's consider only the step direction and the step number, which comes here in your get value mission, and then you have this, and then get value mission 4. So because I'm making that mission file, I'll be knowing at what value it will be there, those values will be there after how many commas and at what index. So I got these two values. Now what I will do is I'll pass it to my stepper motor function. Now what a stepper motor function does is, let's say for example your direction is 1. When I said, that's why I put there 1 for clockwise and -1 for anti-clockwise. So when you have this, you just write the pin, which is direction pin, which goes to the stepper motor drive direction. So there it will be saying that, okay, this is now high, it means it has to go in the clockwise direction. If it is low, it has to go in the anti-clockwise direction. And then you have this number of steps. So number of steps means, how many steps you want to rotate. So let's say when I say that, okay, you want to rotate 90 degrees. So generally this stepper motor, they have this 1.8 degree step angle.
Mm-hmm.
Okay. So when I say 200, it means it makes 360 degree.
Okay.
Okay. So when I say 200, it will make, because 200 into 1.
So then you should have set 50 steps, right?
Sorry? No. So I'm not setting that step. I'm giving that as an angle.
Okay,
I'm already encoded it.
Okay,
So just to check that that it's doing that or not. So what I did is I was putting 90. It means 90 degree actually, and then I have encoded it in such a way that only that command will go there. 90 into multiplied by whatever the factor, that 1.8. So let's say for 360 you need 200 cycle. So for 1 degree you need 200 upon 360. Then for these many numbers, how much you want?
It should be 50 cycles, 50 steps, right?
50 steps.
So how is that becoming 50 here?
No, so wait, I'll show you what it comes here. Just a second. Yeah. Yeah. So you have, when we say that 90, it converts that into, that number of steps, and then it goes in there. So this is what we are encoding it here. Actually, initially I thought that I have done it here, but this is what so this is how our publisher node look like.
Subscriber. Publisher.
Publisher, yes, sir. So this is running on the Pi. So this is what I'm doing here. I'm just simply making this our mission string. Okay. So I have the speed, I have direction, I have run.
This is running on the Pi.
Yes, sir.
Okay.
So this runs on a Pi, and here it runs on the Arduino.
Okay. So once you read it in, can you go back to the point where it was reading?
Yes. So okay. So here we are reading it, the step direction and the step number. I have converted this here. Okay, that
1.11 is
yes.
key factor.
Yes.
Okay.
So
Alright.
and then you pass it to this here in this stepper motor function, because I'll be calling it here in our loop somewhere here.
With the rudder angle and the rudder direction.
Yes.
Okay. All right.
So this is how our stepper motor works for the command.
Okay. Can I also look at one example for the BLDC motor?
Okay.
And that will, I think, cement it off.
Okay. So let's say for BLDC, you say that forward, and then you said that, and then you said the RPM of the motor 70, which is like a duty cycle right now here, and then that's it. So this, it comes here. So you have this speed value information, which you are getting it from the data, because if you see the string which I am making here is the first one, this speed, direction, run, and then so we got this speed value, you got the direction here, and then the break is just like a start and a stop. So once I receive the string, I'll compare with each character here. So let's say, for example, I have this F. So it means you go with the forward speed. Now, forward speed, to make it forward direction, you have to make the drive pin which shows the direction, you have to make it low, because it works on a low level logic if you want to go there. So we are making it here low, and then we are not saying, we are saying a start. So it means that again it will make the 8 pin. It means the start stop pin of the break pin of your drive, which it will make low again. Okay, and then you put the RPM value. So this is where you are reading the RPM value, and you are writing this to the pin number 5, which is analog.
Your sharing has gone away. Am I audible here?
Yes, sir, but Awanish's screen is please.
Okay, Awanish will join back in. I think there was some issue. Where did you guys lose him?
Like just now, like last when you said that his screen is not now.
Okay.
His screen sharing is not now.
Okay. So you were able to see the forward and reverse and the start and the stop part of the
Yes.
code. Okay.
Sir, we can't hear. The mic is off.
Sorry, the mic is mute.
No, sir, he's not audible.
Hello.
Yeah, now you are audible.
Hello. Yeah.
Yes. Yeah.
Okay. Right. So this has to be in some number, right? When we say that we want to move at that RPM, so that RPM has to be in some number between 0 to 3000 RPM, because that was the maximum RPM of our motor is. So when you give that RPM so when we convert there and we are transferring over serial port, it converts it. I mean, we have to send it in a string form. So we get it in a string form, we convert it into the int value, you can convert it into double value and all that. But here what it is like, it's a whole number. I mean, we are not putting in some point and all that. So this is what we are doing. We got the speed information, and then we will do this function, this analog write, which writes on the pin number 5, which is like a PWM pin, which has the capability of generate the PWM signal. So you write analog write pin number 5 and the RPM value. So here we are giving 70. So it is like a duty cycle value right now. So this duty cycle value, it will write with that the PWM signal on that pin.
So, but if at a later point we want to change that to an actual RPM value rather than a duty cycle, you'll have to create a function.
Yes.
Which will say BLDC motor, where you take in this RPM, convert it into a appropriate duty cycle,
Correct.
and then you write it to the analog pin 5.
Correct. Yes. Correct. So I mean, we have to encode it in a way. So 0 to 5, it will show 0 to 100 duty cycle, percent 100 duty cycle is like 0 to 3000 RPM. And we map it and then
We do the math.
yes.
Okay. Okay. So I think that comes to the end of it.
Yes, sir. So yeah.
All
Probably,
right.
yeah. So here already we got this one. So
This is the one which is running on the pipe.
yes, sir.
Can you also show the subscriber running on the?
Yes, so
Oh, subscriber is running in the Arduino.
Arduino.
Okay.
So and what Vishwa did, now we have to implement that also in this one. So he already done this one. So what we need to do is, probably I'm not good at the ROS yet,
No,
but
we
I
won't
think
do that
it's
here. No, we won't do that here.
no. I'm just saying that probably we have to just
It will be a
subscribe to
separate
the
node.
yes, yeah. That will be a separate node.
Correct.
But again there will be control signal, and then you come here and
So
then
you
do
will
that.
subscribe here to another node
That's
from
right.
Vishwa.
Yes.
So once you subscribe to the sensor node, then you can do things here.
Yes.
Before you pass on your mission.
Right. Yes.
Okay. All right. All right. Now is the time for the questions. Last couple of minutes. We are going to wrap up now.
Yes, sir. I have one question, sir.
Go ahead, Shadab.
Sir, while using the BLDC, will you consider the use of the feedback system in it?
Sorry, feedback system.
Yes, feedback system.
He's asking whether there is a feedback mechanism from the motor itself. And the answer to that is no.
No,
There is no. So typically, if you wanted a direct feedback from the motor, you would need an encoder on the shaft of the motor, which can then give you the RPM value.
Yes, tachometer.
Tachometer, which is not there right now. But the feedback will come in through the sensors. We are not really so importantly controlling the speed of the motor, but rather we want to control the speed of the vehicle, which can be achieved using your GPS coordinates fused with your IMU estimates. Did that answer your question?
Yes, sir. And sir, while using the direct feedback control system, we can reach the same conclusion as well, I think.
What do you mean by the direct feedback? Feedback of which signal are you talking about?
Sir, the vehicle speed directly we can calculate it and compare
Yes, that
it with
we are
the.
getting through, that we are getting through the GPS here. The GPS tells you where you were, where your local position was. The motor can't tell you. See, that is the problem between the wheeled robots and the marine robots. Here, if your propeller turns by 1 RPM, that's very hard to tell where exactly you are based on that. You can't encode your RPM to where your position location is. Whereas on a wheeled robot, you know if my wheel has turned by so and so amount or 360 degrees, I must have moved forward by 1 circumference of my wheels. Is that making sense?
Yes, sir. Got it.
So since that cannot be done here, the only way we get feedback here is through the sensors, through the GPS system. All right. Any other questions or any follow-up questions?
So no questions. Great. You guys understood everything.
Either you guys understood everything or you didn't understand anything.
Oh, then it will be my bad.
All right. Okay.
I got it.
Jokes apart, any other questions?
Vishwa, I know you. You don't want
Yes. Yes, sir.
You don't have
No, sir. I understood. Yeah.
Okay.
Okay, all right. Thank you very much. The person who started the recording, can you be kind enough to stop the recording as well?